So in this video lecture, we'll discuss how optimization has been implemented for variational approximation in a number of different ways, and we will also look at examples of how these approaches have been used for some example problems. So as we've seen from our previous video lectures, one of the key ideas behind variational approximation is that we are solving an optimization problem. We're not directly solving an inference problem, but instead we're looking at how we can formulate the problem to be solved through optimization. There are other optimization-oriented approaches that are used in machine learning, and we can look at these. One of them is support vector machines, where we're looking at separators, linear separators in a high-dimensional space that we can use in order to create better classifications, for instance, in support vector machines. Neural networks also use optimization. This is actually relatively simple to express but hard to implement, but neural networks are very effective in their use of optimization. Trees, decision trees like random forests, use optimization. So optimization is a real strong place in machine learning, and it has a lot of advantages. We can use things like stochastic gradient descent, which has proven to be something that can scale very well, and it's particularly useful in deep learning approaches. Good optimization methods exist in addition to stochastic gradient descent, like conjugate gradients and others that can be used to get fast results to optimization problems. The key thing about optimization is it scales with both the data and the model, and by this we mean we can have a lot of observations, millions of observations or tens of millions of observations. And the model, it can have many parameters, tens of thousands, hundreds of thousands, possibly even 1 million parameter values, and we can solve these with optimization. It also allows for a more explicit trade-off between bias and variance, and by this we mean we can explicitly incorporate regularization into our optimization problem. It also mathematically represents learning. You can think of optimization as an attempt to improve performance, and in this sense, it's learning. It's learning to get better. It's learning to make the models better as we progress through the optimization. We can also explicitly measure algorithm performance. We can look at how close we are to an optimal solution versus Markov chain Monte Carlo, where we really don't know. We have no way of guaranteeing that we've run our chains long enough. We just look visually at trace plots and attempt to get an assessment of whether or not convergence has occurred. There are disadvantages to these variational approaches. They only approximate, and they're not as good an approximation as, for instance, Markov chain Monte Carlo. Typically, they're only good for a series of unimodal approximations that are put together to create the overall result that we're looking for. So that means that we can get stuck in local optima. The theory is being developed. We've given you the real foundations here using things like the expectation maximization as a framework for understanding the foundation behind it. And we've also shown you the key features such as the Kullback-Leibler minimization and the maximization of the elbow or the lower bound. It can get stalled, as we pointed out, and stuck at local optima because it does use only unimodal approximations. And although it's model agnostic in principle, when we formulate the ideas behind variational approximation, it seems to be model agnostic, but only a few somewhat generally applicable libraries are available right now. So it's difficult to implement. You have to actually spend time to implement the optimization. So let's talk about some of these libraries that are available now because they represent the ongoing approach. And bear in mind, by the time you hear this, there may be other libraries that are available or other packages available that will make it even more model agnostic in implementation. But for right now, these are ones that we know about. Streaming variational Bayes developed in 2013. Black box variational inference developed in 2014. We're going to say more about this one in a minute. automatic differentiation variational inference, or ADV. We're going to say more about this one. This was developed in 16. And normalizing flow, developed in 15. Some common elements to these: stochastic gradient ascent is used in all of them. A mini-batch approach to stochastic gradient ascent is used in order to make things go faster. So let's look at black box variational inference, or BBVI. This automates the setup and computation for variational inference, so it's trying to be what we want it to be, model agnostic. It's been implemented in a package called Edward, and it uses TensorFlow. And it was bought by Google, and there's now an Edward 2. But Edward 2 is not widely available yet. So as of this video, Edward is available, but Edward 2 is not as widely available. Although, as I said, by the time you listen to it, it may be more available, and it may be something that people are using more than they were at the time that I recorded this video lecture. The user provides a probabilistic model and data, so there's the model agnosticity. You don't have to get in and write the code for the optimization. It uses an estimation function to compute the gradient of the elbow. So it's an estimation function in order to find the gradient and do the optimization. The expectation is over the latent space, and it's approximated with a Monte Carlo integration. You only need to be able to compute the joint of the variables, both the observed and latent variables, in order to run Edward. Okay, then there's another approach, which is called automatic differentiation variational inference, or ADV. And this is actually the one that we will show some examples of its use. And it automates the setup and computation for variational inference, so it is trying to be model agnostic as well. Its implementation is in the package PyMC3, which we've been using in this course and will continue to use. And it uses, instead of TensorFlow, it uses Theano as its tensor library. The user provides the probabilistic model and data, so again, it's model agnostic. It maps the support of the latent variables to a new space, to the reals. So what this means is that it's an unconstrained optimization. It does not solve a constrained optimization. It takes a constrained optimization problem and maps it to the reals. And we'll denote that here as Z tilde to indicate that this is a mapping from the original space to this unconstrained space. It then approximates that joint distribution of these latent variables in this unconstrained space with a Gaussian. You can use other distributions if possible, but this is the basic way that it runs and the easiest way to make it run. But you'll see that inverse transformations from Z tilde to Z are in fact non-Gaussian and return it to its constrained space. It uses reparameterization to allow computation of the gradients. And expectation of the latent space is approximated with Monte Carlo integration, very similar to what we saw in the Edward package. It does require differentiable models, and this is this is something that does constrain its use. So these are the major packages and techniques that are available right now for doing what I do call model agnostic variational inference. For other problems, you're just going to have to write your own optimization code using, again, the principles that we've described earlier. And it's possible to do. It's just it'll take you longer to build it, but it is entirely possible to do it, particularly in languages like Python. So let's now look at some code and some examples that we've implemented with that code. So notice here that we've loaded some additional packages. We've loaded PyMC3. Of course, we've been using that throughout the course. We've loaded the Theano package, which PyMC3 is going to use now, the tensor package it's going to use particularly for this optimization, and we've loaded TensorFlow. So the first example we'll look at is an example of a beta binomial model, and we'll set up some data that we see there It's our typical beta binomial where our likelihood is a binomial, our prior is a beta, and so we're going to see if we can model this with a variational approach as opposed to a MC approach or a conjugate gradient approach. The advantage to this, of course, is since it is a conjugate gradient example, we know what it should be. So we can compare the result we get with a variational approach to what we get with what we should get optimally with the conjugate approach. So here's the picture. We have a beta distribution on the left shown in blue. This is the posterior distribution. We have the prior distribution shown in a dotted line, and you can see the prior is just a uniform distribution, which means it's a beta 1,1. Now this is a constrained problem, so this is an example of what it is that this ADV approach doesn't like. It actually has to work with an unconstrained problem. So what it does is it converts it to an unconstrained parameter space, and that's what we show on the right-hand side. So the unconstrained distribution shows what happens when we take those two beta distributions and we put them on the reals. Both the beta distribution representing the prior, the dotted line, and the beta distribution representing the posterior. So we run the variational model, which is called PMFit. We run it 40,000 times using this ADV optimization method, and we're going to give it the random seed we set at the beginning, and this allows us to obviously repeat our results over and over again. We'll get the same thing so that we can see, we can measure our results. We can ensure that we're going to get the same result each time. And of course, if we want to try it with different random seeds, you can do that and just remove that random seed setting. So here's our elbow plot. This is an interesting elbow plot in that it actually starts out with higher lower bounds than we end up with it at the end. But you can see that it converges. Although the convergence is not great, there is convergence to a solution that we can use for estimation. And here are the results of the estimation in the unconstrained parameter space for the posterior distribution. And it's shown in red on the right. And you can see that it does a pretty good job of approximating the unconstrained posterior. And in these plots, in the plot on the left, you can see that it does a good job when we reparameterize it in terms of its original space, between 0 and 1 that the betas are in, the posterior distribution in blue, and the approximate distribution in red. You can see the approximate distribution is pretty close to the original unconstrained or constrained beta distribution that we wanted to approximate. Okay, let's now look at another example, and this is an example of attempting to estimate a density across a number of points in a space, and it comes from a data set on LiDAR data in this book by Larry Wasserman. Shown in the one cell is an example of what the data look like. You can see it has two values, range and log ratio, and these are what we're going to attempt to model. And here's what the data look like. They look like this clear pattern within the two-dimensional space that we have for our data, but it's clearly nonlinear. And the question is, how do we model this in an effective way? Well, there are a lot of ways that you can do this, and I'm sure you've seen spline fits in the regression class and other things like that. But here what we're going to do is we're going to model it as a series of linear models, and we're going to put them together as a mixture. So we're going to show that you can do this mixture of models idea that we mentioned. In addition to a mixture of Gaussians, you can do a mixture of models to produce results. And this variational approach will give us a good approximation of what this fit should look like. So here's the basic idea. We're basically going to put together a series of linear functions, and the question is, how far do they go how far does each model go in fitting the data, and where does it join with another model, another linear model, in order to make this fit as close as we can get to the data that we see. So as we said, we're going to solve it through a mixture approach, and here are the mixture weights. We're going to call those pi, and we're going to put them together through what's called a logit stick breaking approach, which means that we're going to have a series of functions that describe the logit as to whether or not what the value should be for each one of those weights, and that weighting is going to be determined by a logit function, and we're going to represent the parameters here as alpha and beta and give them prior distributions that are Gaussians, standard Gaussian distribution 0, 1s. So the component models are going to be regression models where y will be the representation on the y-axis and x will be the data on the x-axis. And they'll have parameters gamma and delta and also tau, gamma being the intercept term, delta being the slope, and tau being the precision. So then the observation model will be a mixture of these, where the pi's are the mixtures that we represented before as this logit, and the y's are going to be representing each one of the regression models that we have. So we're going to have a mixture of these regression models, and that'll be our way of solving for this particular estimation of this data set. So we run the ADV optimizer to get a fit using 40,000 iterations of the algorithm. And shown in the plot, you can see the elbow curve, and this one looks very nice. It looks like we've got good convergence to a lower bound for this particular problem. Now what we do is we sample from the posterior distribution in order to get a sense of where the breaks are, so that we can get a sense of what the weights are in our mixture model. And you can see that we put in for 20 of these, but it turns out that we didn't need that many. It turns out that we needed only about 11 of them at most, and clearly beyond 11 the weights are effectively 0. So we also, using this variational approach, solve for the size of the mixing weights. In a sense, we overestimated them at about 20, and the variational approach gave us an estimate as to what the mixing weight should be. This is a very nice property of the variational approach, that we can use it to get the number of mixing components as well as their weights. And the weights are shown in the distributions, or in the plot that we have here for the expected mixture weights. So we can also use the sampling that we did of the posterior distribution to plot the mixture result, the mixture model result. And you can see it does a very nice job of estimating the data. We've also shown in this plot the 95% confidence regions for this particular estimation. And again, it does a nice job of representing the data. So these are two examples of how we can use variational inference to solve real problems in Bayesian machine learning.